Recording? Yes.
Okay, just let me know once you see the screen so I can start.
Yes, Dr. Esaú, I will see the screen.
Okay, perfect.
Yeah,
well,
thank you very much.
Thank you, Satya, for the nice introduction. Right now, I'm here at, as you mentioned, in India, doing just a sabbatical stay. Yeah. And today I have a lot of material. I will try to be quite brief, just to have don't consume my time. And the title of the talk is about text representations and language models. So basically, what's happening? Okay. The outline of the talk will be a brief introduction. As I understand, you already have some previous session where you discuss some NLP basics. So I will try to be short in this part. Some general concepts. Specifically, I will speak about supervised text classification, which is the main point that I will be describing here, and then the most extent part of the talk is about text representation, as the title of the talk. I will describe some traditional text representation techniques. Some people call these old school techniques, and some concept-based indexing, and then we will go to word embeddings and very recent language models. During this description of this type of representations, I will show you a few examples or cases of study where we have applied some of these techniques and the results that we have obtained. And finally, some conclusions, some final remarks, perhaps some points that to give you something to think about after this talk. Okay, so why to work with language? I guess that all of you that are here now, you are really interested in language. As humans, we are systematically generating resources, and for that we need a technology that helps us to organize, to retrieve, or to search this type of information. As you all know, all the communications that we have are in form of written documents. We also have a speech. I understand that tomorrow one of my colleagues will be speaking about speech processing. Also, we have signal languages or gestures or corporal language, even artificial language. So for processing all this type of information is why we need automatic tools that are able to handle natural language. One definition that I really like to mention is this one from Cole, which I think is still very valid. Yes, which is human language technologies. This Ronald Cole defines human language technologies as a multidisciplinary field that requires expertise in areas of linguistics, psychology, engineering, and computer science, of course. The main goal of this type of technologies is to generate or to enable people to communicate with machines using natural communication skills. This means that we don't need to learn, or we don't need to adapt to the systems, but the systems need to adapt to our language. Okay, what is the dream of the natural language processing field? Perhaps you already see something like this before. The entire pipeline is, for example, assume that I have my latest flashlight iPhone or something like that in this end of the figure, and I need to know what is the local time in Bhubaneswar. I say that correctly? Yes. Yes. So ideally, this automatic entity should tell me the exact hour in this geographic area, right? But in the process, we have many challenges involved. For example, the first one is how to convert a speech to a text, right? I will not speak about that, but once we have the text, we need to obtain the morphological representation, Then we need to obtain perhaps the syntactic representation and then a semantic representation, which actually conveys the meaning of the message. Once the computer has understood the meaning, this entity should be able to tell us the answer or to give us the information that we are requiring. But as you might imagine, there are many problems in the process, right? The first one and the most important one is the ambiguity associated to the language. This means that words can be interpreted or understood in more than one way. Also, the context play a very important role in resolving the ambiguity. And we have many different types of ambiguity, for example, lexical ambiguity, syntactic ambiguity, and semantic ambiguity. I will give you a brief example for here. Given the query Paris Hilton, perhaps are we really interested in the actress, this Paris Hilton, or perhaps we are actually looking for information for the Hilton Hotel in the city of Paris. So that could be an example of ambiguity. Tiger Woods, maybe we are looking for something related to wildlife, but perhaps some other users might be interested in knowing something about the famous golf player. So what is the main conclusion from this is that simple word matching usually fails in most of the automatic systems. Examples of lexical ambiguity, which you can see here, for example, plants need light and water versus each one plant one. In the first sentence, plants is used as a noun, while in the second one, this plant is actually used as a verb and is the same word, right? Or the second example, the fisherman jumped off the bank and into the water versus the bank down the street was dropped. So the same word with different meanings. Or syntactic ambiguity. For example, he ate the cookies on the couch. What is the exact meaning of this? That this person was seated on the couch, or the cookies were in the couch when he ate them, right? So this is actually very complex problems to solve, and I will say that even recent technologies have some complexities and difficulties in solving this type of task. But what we have so far, the truth is that there are many problems involved in the full pipeline, and if on top of that we add that probably users or untrained users will face more difficulties because, for example, common or regular users, perhaps they don't know how to build good queries. For example, Google, right? If you don't write the correct query, perhaps you will get a different set of results. Or if you are using some automatic assistant, how to speak to this assistant? I mean, do we need to speak properly? Do we need some specific accent? This, for example, in Mexico, this happens when these automatic assistants came for the very first time in Mexico. They were trained in Spanish from Spain and not from Mexico. And so the system didn't work for anything because although we speak Spanish, it's not the same pronunciation, not similar, right? Okay. And this problem becomes more evident in low resource languages. Perhaps my colleague Shantipria will tell you more about this in his talk. However, well, what is also a fact is that recent research has allowed the generation of highly capable applications that are actually able to solve or to work with language. There are two main approaches that during this, since the beginning, two main approaches have been followed. For example, the first one is understanding the language. What is the meaning here is that actually to build technology that understands or that gets the meaning of the message through the words. And the second approach is manipulation of the language, which is taking advantage of the regularities of the language in order to solve particularly tasks. What we are going to talk during this presentation is mainly about manipulation of the language. Here, a small note, I will recommend this reading for those of you that who are interested in knowing more differences regarding manipulation and understanding. This is a very recent paper from ACL 2020. Okay, so a brief description of general concepts. This is, okay. When we are talking about natural language processing, there are a set of steps that are crucial for every task or almost every task, which is, for example, preprocessing, which means removing all the information that perhaps is not necessary for this automatic entity to solve some task. Then we have the indexing stage or the representation stage, where we actually get something that the computers are able to understand. And finally, some dimensionality reduction step, which is also part of the pipeline, because as probably many of you know, when we are dealing with documents, with text documents in particular, the dimensionality of the representation is usually in the number of thousands of features, which could be a problem, especially if we don't have enough computation power. So the general idea of what is there to represent is that we need to take raw documents and generate a representation that is useful for some posterior task, for example, a classification task. What is text classification? And I will focus only on this definition because during the rest of the talk, we will be describing many types of classification, text classification problems. So what is the basic idea? Given as input a collection of documents that perhaps are from the same type of category, for example, news articles, the idea is to generate an organization of this document, perhaps based on the content of these documents. For example, which of these documents speak about sports, about politics, about economic or religion, etc. So basically, this is the definition of text classification, to organize documents into a set of predefined categories based on their content. So what is the meaning of supervised classification? Well, I think all of you will be familiar with this. So given a universe of objects and predefined set of classes, we need to assign each object in the correct class. So given an instance X from and a representation vector or a vector of measurements and a predefined set of categories, we need to find this function that helps us to determine the category of every instance in this space. So if we wanted to see this visually, this will be the pipeline of many supervised text classification approaches. We have an offline stage, which is the part of the figure, where we have documents and labels. We obtain the representations. With this representation, we train some machine learning algorithm, which is used in an online process where we need to determine the category of a new document, right? So I guess there is nothing too complex here. How do we evaluate this type of pipelines? Normally, we have to perform many experiments. For this, we normally require training and test partitions, or if we don't have this, perhaps it's normally to apply a cross-fault validation strategy. So like the basic stuff in machine learning. What metrics are useful for this? Well, I understand that all of you are familiar with this type of metrics: accuracy, recall, precision, and F-score metric, which at the end, all of these metrics give us an idea of how good is the performance of some automatic classifier, given that we know the real levels of some data set, right? Okay, so with this, I finished this general part of the concepts, and I will go now to the important thing. We will talk now about text representations. I would like to thank Manuel Montes, which he provided me some of this material some time ago for preparing some course in the university. So, okay. The very first basic type of representation is the vectorial space model and the bag of words. So as we mentioned already, the first step that we need to apply when we are solving some NLP task is to transform the documents into a representation that is suitable for, in this case, for example, for a learning algorithm, right? The most common use document representation is the bag of words approach. What is the meaning of bag of words? Well, basically, as you can see in this figure, we don't care about the order of the words. We just put every word is considered as a single feature. And we will have as many features as many tokens or different tokens we have in the document collections. Some of the characteristics of the bag of words is that the order of the words is not captured by this type of representation. There is also no attempt for understanding the content of the document, right? This type of representations doesn't take any semantics into consideration. What is how visually looks this type of representation? It could be something like this. At the end of this type of generating this representation, we will have some big matrix like this, where every row in the matrix will represent one document. We will have one vector for every document, and every column represents the set of different words. So we will have as many, as I told you before, we will have as many words, sorry, as many columns as the size of the vocabulary from the document collection. And here, as you can see, we have a W value that indicates the contribution of the word J in the document I, right? This once we have this type of representation, it's very easy, very simple to compute document similarities, because once we have this type of representation, we can actually move everything to this vectorial space, and we can determine document similarity using traditional metrics, for example, the Euclidean distance, as you can see here, or we can measure the cosine similarity. And intuitively, these metrics will give us an idea of how similar two documents are in this vectorial space, right? How to determine the best weight for every in this matrix, this W? How to better determine this W? Actually, there are many approaches. The two main ideas that are part of the bag of words is, on the one hand, we have to consider the importance of a term based on the number of times that it appears in the document. This is a term that appears frequently in a document. It's possible that it will help to describe the document content. And on the other hand, if we have terms that appear very frequent in the entire document collection, we will call this like very common terms. These terms will have to end up with a weight, very low weight, right? Because actually they don't help to discriminate between different classes. For example, stop words could be an example of very common words that appear very frequently in every document, and they not necessarily need to have a very high value in this W weight. So what are the main or the traditional weighting schemes? Probably you know some of these. This is the binary weighting scheme, where this W is set to 1 if the document contains the term, or 0 otherwise, or we can actually measure the frequency, which is related to the first part that I mentioned in the previous slide. Like the W is defined as the number of occurrences that this term has in the document I. Or this is also a relative weighting scheme, which is also known as TF-IDF, where the idea here is how to combine these two ideas to determine the correct weight according to the number of occurrences of the term in the document, and also considering the number of documents that contain this term. Actually, the TF-IDF is, I would say, is one of the most frequent even nowadays for representing documents. What are the main limitations of this type of representations? Well, as I already mentioned before, there is no information on the word's positions, so we lose the order of the words, and that could lead to semantic problems, because actually there are nothing related to semantics here, and also two main problems, which is synonymy. This could be, for example, that words that have different meanings, for many ways to refer to the same object, which is, for example, car and automobile. In this type of representation, car and automobile will have a different column in the representation. And polysemy, which means that many words will have more than one meaning. For example, model, bank, or cheap. So this type of problems normally leads to poor precision, while synonymy leads to poor recall values. Okay, so there are actually many extensions for this type of representations that actually try to solve this type of limitations. For example, there are, and well, actually I mentioned these three ones because we will speak about these three in this during this talk, which are distributional term representations, concise semantic analysis, and more recently word embeddings, context independent and contextual embeddings also. So, but before going into the first one, which is distributed term representations, I will describe some I will describe some of the ideas that have been tried in the past in order to solve this type of problems. For example, some of the ideas people think is to generate this representation is, for example, including post-tags. Post-tags is a label that indicates what is the function of the word in a given context. For example, in the plant example, we can the idea will be to have two different columns for the word plant, where in the first column is used as a noun and the second column is normally used as a verb, right? This is a simple, nice idea. Actually, it works, but there is an associated problem, is how do we determine the post tags, which is actually very complex, also very complex tags. Indexing with post tags normally improves precision, but reduces recall in some experiments that people have performed before. Well, as a main conclusion here, probably post annotation is not worthy as a standalone indexing strategy, even if this post tagging is performed manually. There are some associated problems that actually is not necessarily worthy. Okay, so what is another idea is okay. As we have seen right now, until now, is that using single words as index terms generally has good exhaustivity but poor specificity due to the ambiguity. But there are some words associations that have different meanings if they are considered by separate. For example, hot and dog. If we hear this, hot dog, especially in America, this is related to some food, right? But if we see these words separated, they don't actually mean anything. So this is like fixed expressions or fixed index terms, we will say. So one of the ideas that was proposed to solve this type of problem is to use index as index term more complex phrases. For example, the Bank of Cien and the Bank of Japan. This will be some example of phrases that could be used can be used as index terms. So the idea is the same. So we'll have a big matrix where every document has a vector, but instead of single words, here we will have extracted phrases from the document collection. So now here the question is what type of word sequences or phrases are more relevant, and how to extract them, right? So, which is also not a simple task. There is something called syntactical phrases, which is some approach that has been tried to identify these phrases. For example, consider this example. This apple pie looks good and is a real treat. So real treat has a particular meaning in this way, combine. Apple pie also is two words combined. This subject-verb relation is pie looks, or verb-object relation is treat. So this type of relations are obtained from a syntactical analysis, which is also part of some post-taggers generate this type of information, which is called the syntactic tree. That could be helpful in order to identify this type of phrases. Another idea will be to use name entities as index terms. The problem with name entities, well, for those of you that perhaps are not familiar, name entities is the task of identifying names of persons, locations, organizations, mainly in documents, automatically to detect this. So, for example, when we find the word George Bush, we will know that this probably is related to a person, or when we find the word Mexico, probably is related to a geopolitical place, organization, sorry, or a location. But here is also the problem of, similar to the post tagger, now how do we determine the name entities, right? So a different idea, but in the same direction, is using n-grams as index terms. N-grams are defined as subsequence. It's a subsequence of n items or words from a given sequence. Actually, we can have word n-grams, which are sequences of words, or character n-grams, which will be sequences of individual characters. The good thing about n-grams is that this type of units are very easy to compute. It's very fast and easy. And if we combine n-grams of different size, we can produce, we will get a good trade-off between flexibility and performance during, for example, during search time. One of the main problems that is associated with using n-grams is that normally we will have high dimensionality. Actually, this is very exponential. Using bigrams, if we already have a large vocabulary, once we include bigrams, this grows like in an exponential way. Trigrams or 4 grams is also very, very costly in terms of representation size. So here the question is how to reduce this dimensionality, or how to select the most useful n-grams. One of these ideas to identify those phrases or n-grams that perhaps are more discriminative during classification tasks is something called maximal frequent sequences. The idea of maximal frequent sequences is to identify those sequences of words that are actually frequent in a document collection and that are not contained in any other longer frequent sequence. The main advantage of this type of indexing term is that avoids storing numerous less significant phrases. But the problem with maximal frequency sequences is that actually is also is a very costly approach. I put here one reference for those of you who are interested in reading something more about this. Okay, now we have mentioned a few traditional techniques for document representation, and I will describe some of the work that I did with one student in Mexico, which is plagiarism detection. So in specific, we are in this work, we face the problem of paraphrase plagiarism identification. What is the definition of the task? Is to automatically recognize the document fragments. This is part of the document that contain reused text. This text is intentionally hidden by some other user, normally using some rewarding practices such as semantic equivalences or discursive changes, morphological or lexical substitutions. Identifying paraphrase plagiarism is also considered a very difficult task, even for humans. So in this work, was published actually in 2018, I think. The main hypothesis that we propose here is that when some malicious user is doing some plagiarism action, it's very difficult to remove the original author's writing style. We say that there is some author writing style fingerprint that prevails even in the plagiarized text, even after some paraphrase operations. So for this, what we did is to propose a novel text representation that considers both the content and the style characteristic of the text in order to represent these documents. And we do this considering character level features. So for the idea is to use or to distinguish between types of n-grams. And I put here the reference to one paper that gives us this idea. Basically, this paper says that not all character n-grams are the same. We can distinguish these character n-grams into like broad categories. For example, I put one example here. This is the sentence. The n-grams type analysis is useful for understanding how the method is working. So in this case, we consider 5 categories of character n-grams. For example, punctuation means all those character n-grams that contain some punctuation mark. As you can see here, these n-grams are extracted from here. Inner words are those n-grams that are part from some words in the middle, in the beginning, or in the end. We have between words, which is the connections only between different words, prefixes and suffixes. So, for example, how do we capture style using, for example, suffix and prefix and also punctuation? How do we capture content features with inner words categories and between words categories? So the idea here, okay, before going to the results, the idea here was to represent text fragments only by 6 features. Actually, what are those 6 features? Are the similarity between the 2 text fragments in terms of punctuation n-grams, inner words n-grams, between words and prefix and suffixes, right? And the 6th feature was considering the entire set of n-grams. So for this method, we try several traditional indexing strategies. For example, you can see here, this is some baselines that we evaluate. Traditional bag of words, traditional bag of words of n-grams of size 2 to 5. We also consider these most frequent common subsequences. We also consider some state-of-the-art methods which are structural based. For example, considering only stop words n-grams, or part-of-speech tags engrams. We also evaluate with some knowledge-based approaches that use WordNet to extract, to trying to extract meaning from the fragments. And we evaluate some ensemble strategies with this data set, which actually is called the P4PIN data set, where 800, more than 800 paragraphs are considered plagiarism, and the rest, more than 2,000 are not plagiarism cases. As you can see, we are reporting F score. This is the baselines, and for the method that we evaluate, we actually obtain very good performance, even though it's a very simple representation. As you can see here, for example, this is the best baseline, and we evaluate the robustness of our approach against different type of paraphrases. For example, to semantic changes, morphological, discourse, syntactical, etc. So in all the cases, we obtain actually very, very good performance. And if we compare our approach with the best baseline, which is actually based on longest common subsequences, this is the performance from our approach. Is near 93 F score in general, which was actually quite good. And this paper has been referred very frequently due to these results. So what indexing type is better in this scenario? Well, normally something that I usually say to my students is the best choice is task dependent. The first step we need to do is to get to know our data. Normally this happens, people get surprised that for some real life task, traditional indexing strategies like the ones that we have described so far represent very hard to beat baselines sometimes. Right? However, well, something that is the reality now is that every time we have more access to more data, to bigger document collections, and well, there is a big hype towards this big machine learning strategies based on deep neural networks. Sorry, someone speaking?
Mute yourself.
Okay. So,
continue, sir.
well, yeah. Okay. So more recently, well, approaches based on word embeddings, well, have shown important improvements also in this type of task. But before going to word embeddings, I will go first before we'll go describe concept-based representations. The main hypothesis of this type of representation is that basically the semantic of a term can be inferred based on the terms that are frequently appearing close to these terms, or very near into these terms. And there are three big types of representations based on this hypothesis, which the first one is the document DOR, which is document occurrence representation. Here the idea is that the semantic of a document is conveyed by the words that occur in it. The other one is T-core, which is term co-occurrence representation, that here is basically says that the semantics or the meaning of a word is conveyed by the words that commonly co-occur next to it, right? And last are the second order attributes, or SOA representations. Here, actually, the idea is that the meaning of a words and text fragments can be inferred from the relationship with predefined concepts. And I will try to describe very briefly every one of these. Then I will show you some case of study where we have used this type of representations. What are the advantages of this type of the representations, the concept-based representations? Well, contrary to traditional indexing representations, the bag of words, let's say, the dimensionality of this type of representation is actually determined by the amount of concepts normally, or then the amount of documents. We will see that in a few minutes. This means that the dimensionality will not grow with the vocabulary of the corpus. So we will have at the end less sparse representations or more dense representations, if you wish. Most of these techniques generate an intermediate word representations. What is the meaning of this is that some intermediate step we will have word representations. And with that, we can determine actually semantic similarity. Another advantage of concept-based representation is that they consider the order of the words. So contrary to bag of words, here the order is very important. And actually is that important that will help to define the semantic of the words. Let's start with the first one. So document occurrence representation generates some matrix like the one that we see here. We have terms as rows, contrary to bag of words. We will have the terms as, we will have one row for each term in the document collection, and the columns represent the documents from the collection. Here, this W indicates the contribution of the document to the semantics of the corresponding term. What is the intuition behind these W weights? Well, the idea is that the more frequent the term E occurs in document J, the more important is the document for characterizing the semantics of TI. And the more distinct the words that document DJ contains, the smaller is the contribution of this document for characterizing the semantics of the term TI. So at the end, well, I put the reference to this in the previous slide here. So if you want to go through the mathematics and all the equations, you can refer to the paper. Now I'm just trying to describe the intuition behind this. So after we generate this matrix, which is a term document matrix, what we have is word representations. So we will have a vector for every word. We don't have document representation at this step. But what we need in order to solve, for example, a text classification task, what we need is document representation. We need a document representation matrix. So once we generate this matrix, what we do in order to generate this document representation matrix is to sum all the vectors from the words for every document. For example, for obtaining the vector of document 1, what we do is to search for those terms that have a different value different than 0 in this column, and we apply a simple summatory process, and that will give us the vector of this document. Of course, there are many ways to normalize this summatory, but this is the basic idea. And as you can see here, this matrix is actually will be the size of the number of documents in the collection and not the entire vocabulary. The second one, the term co-occurrence representation, is, as I told you before, the basic idea here is that the meaning of a word can be defined or can be inferred by considering the words that appear next to it. So here we will have a matrix. At the beginning, we will have a matrix of terms for every row, also terms for every column. Here, this W indicates the co-occurrence value of the term I and the term J. So the intuition here is that the more frequent the term I and the term J occur, the more important is the first one for characterizing the semantics of the second one. And the more distinct words occur with the term J, the smaller the contribution for characterizing the semantics of this term. So here we'll have also a word representation and this intermediate step, not a document representation. And similarly to DOR, in order to obtain the document representation, what we do is to sum all the term vectors for that appear in the document in order to generate this final matrix. Notice here that here we will have actually as much columns as the terms in the vocabulary, but the difference that with bag of words representation is that this representation will be less sparse, means that less zero values will be present. Finally, I will speak about the second order attributes. Excuse me. The idea of, yes, the idea of this second order attributes is actually very simple. Here in the figure you can see is based on the idea that if we know some.
Excuse me, please. Kindly all of you just mute your mic. Kindly all of you just mute your mic. Hello. Kindly all of you just mute your mic.
Okay.
Just mute your mic.
Shall I continue? Yeah. So the idea of this second order attributes is, for example, let's assume we have a predefined set of profiles or categories in the document collection. So we know which documents belongs to one of these categories. So the idea of these second order attributes is to try to determine which terms are more important for every profile here. That way, we will have something that is called a second order representation that generates basically a matrix like this one. So we will have, again, in the rows terms, and in the columns we will have, instead of terms or documents, we will have profiles. And the W here is actually a value that indicates the relationship of the term T1 in this case to the semantics of the profile P1 in this example, right? So what is the intuition behind these values? For example, well, in this case, for each term in the vocabulary, we will build a vector Tj that where every component of this vector is a value that represents the relationship of the term with the respective profile. And the more frequent the term occurs in a specific profile, then we say that this term is more important for defining the semantics of this profile. Similarly, at the end, we have word representations, not document representations. And as in the previous approaches, what we do to generate a document representation is to sum all of the vectors from the words that appear in every document. And then we get some representation like this one. So now we have documents represented in terms of profiles. Okay, so now I will describe some case of study where we actually evaluate some of these strategies. Specifically, this case is about author profiling. So for those of you that are not familiar with the task, author profiling is the task of automatically determining some general categories from the author of a given text. For example, we would like to know his or her age, gender, native language, personality, personality traits, for example. So the idea of this type of methods, they try to model the general sociolinguistic features that apply to a group of authors. And this is based on psychology, actually, psycholinguistics. Psycholinguistics says that the way that we use the language actually reveals a lot of information about ourselves. Okay, so for this work, actually this work was presented in 2013. It's kind of old now, but it's actually a good a good reference nowadays. This is part of the PAN competition tasks. The idea is to determine or to classify users according to their age and their gender. So for this task, what we did is actually to use second-order attributes to represent documents. So basically, what we did is to take the actual profiles that we know that exist in the training document collection, and to generate with those profiles these second-order attributes. Although the idea is very simple, the representation, as you can see, is very simple, very, let's say, cheap, and not computationally expensive. This was the first time that this type of representation was used in an author profiling task. And with this approach, actually we obtained during 2013 the second place during that time. So what were the characteristics of the data? Is data extracted from social media? I think it was Twitter data. So normally they are short documents. We have a large set of documents that are very short. There are many grammatical and spelling errors in the documents, and there is also the presence of slang vocabulary. However, well, something that we can see with this type of representation, you can see in this graph, these are the three different terms: homework, apartment, and marriage. And these are the profiles that exist in the dataset. For example, for this task, we need to distinguish between users that whose age is between, I think, 10 and 19, and the 20s category is between 20 and 29, and the 30s category is between 30 and beyond, right? Something like that. So with this SOA representation, what we can see here is we are showing the membership level. This means this work, how important is for each profile. So you can, this is very nice because you can see here, for example, homework is a word that is very relevant for the people that is between in the 10th category. Apartment is very important for people in the 20s, and marriage is also a word very relevant for people in the 30s, right? So this is the type of interpretability that we can get from this type of representation. So, and these we can use to classify documents. So with this approach, we obtain the second place, and we evaluate this with this method in Spanish and English documents for identifying age and gender. However, well, actually some extension that we did of this work is that we found that the SOA method assumes some type of homogeneity in the documents or in the profiles to represent every profile, which might not be necessarily the case in real life scenarios. For example, okay, perhaps homework is a very important word for people who is in between 10 and 19 age old. But perhaps there are other words that are also important. There are different sub-profiles. That's basically the idea. Perhaps there are different profiles or sub-profiles that can help us to identify more relevant terminology for building this representation. And basically that we did. For example, you can see here in the left side, for example, for the task of gender classification, okay, we only know that we have males and females, but probably some sample of males, they are students, or some of them are gamers. Similar thing for females, right? Probably a subset of these users are students, are working in technology, or housewives, or are teenagers. I don't know. So what we did for this approach, well, for this method is to add a cluster step after the profile. So we have the input profiles that are given in the training dataset, and then we apply a clustering stage. In this, for this work, we apply a clustering of 3, I think, 3 subgroups. And then for each subgroup, we generate, or for each subprofile or intraprofile, we generate the second order attributes. And with this method, during 2014, this approach actually won the first place, similarly in age and gender detection. And this is the type of things that you can observe with this type of methods. For example, using the traditional second order attributes, you can see here, the word semester is very important for people in the 20s, marriage is very important for the people in the 30s, but TV, there is no clear difference, right? Like all of them perhaps have the same interest for TVs, but when we use this intra-profiles representation, for example, we can notice, right, that semester is actually very important for people from the 20s, but there are a subgroup of people in the 10s age that that consider this word actually very important. And similar for the word TV, right? Now we can distinguish that this is very important for a subset of users that are in the between 10 and 19 age old. So this is the good thing about this type of representations. And as I told you, this method won the first place during 2014. Okay, what is does concept-based representation work? Well, normally they represent useful solutions for a number of conceptual matching problems. This is some characteristic that we need to make sure. They capture key relationships information, including causal, goal-oriented, or taxonomic information. There is another approach which is similar, that is actually more frequent to see in many works, which is LSI, Latent Semantic Indexing, or LDA also. The problem with these methods is that they are actually computationally expensive, but the same idea applies, right? If you are interested in knowing more details of the performance of this type of representation in different auto-profiling tasks, these are 2 works that we did in 2017 and 2019. Sexual predators identification. For this work, we evaluate second order attributes, and we compare, if I remember correctly, with latent semantic indexing also. And in this work, age and gender identification in different documents genders, we evaluate all the methods that I described in this section: DOR, T-core, second order attributes, LSI, and even word embeddings, if I remember correctly. Okay. Okay. Now let's go with word embeddings. Well, perhaps this is more familiar for many people because most of the recent work, research work, reports results using word embeddings. This concept-based representation, or even the bag of words representations, or traditional indexing strategies, are perhaps out of the scope for many people. Many people consider these technologies as very old and useless. But as I say before, you will be surprised if you get to know how many companies use this type of technology to provide solutions, technological solutions. The problem, in my opinion, with word embeddings is that they have, well, for start, they require millions or even millions of documents to generate adequate embeddings. This type of representations are generated, they try to substitute symbolic representation as the ones that we described already by something that is called distributed vectors or embeddings. The output that this type of technology generates are usually low dimensionality representations, highly dense, right? They are also capable of capturing syntactic and semantic aspects of the words. Normally, well, although I think I forgot to modify this, particularly word2vec is one of the most famous, but this is context independent. I will describe in a moment what is this. Word2vec actually was proposed in 2013, so it's actually quite old already for some people. And this is one of the most popular techniques to learn word embeddings that uses shallow neural network. Sorry, before going to this, what is the meaning of context independent? I mean, this type of technologies, although they are able to generate, to capture syntactic or semantic information, given a word, they will generate the same vector independently of the context of the word. That's why they are referred as context independent embeddings. More recent technologies, I will show you some of these after, are, for example, BERT, which actually produce different embeddings depending on the context where a word is used. So if bank is used in the context of the financial institution, it will generate some specific embedding. But if bank is used in the context of furnitures of something like that, so it will generate a completely different embedding representation and different vector, right? Okay. As I was saying, word2vec is actually one of the most popular methods. There are many pre-trained embeddings that people can use to represent documents. Word2vec is a very simple neural network that and proposes two different methods, which is the CBOW and the skipgram model. And the first one, the idea is that given a word and the associated context, the idea is to predict the next word. And in the skipgram model, what we need to given some word, one particular word, what we want to learn is to predict the context that will be associated to that particular word. Again, if you want to know all the details of the configuration, I will recommend you to go to the paper, because otherwise I will take longer and it's not the case. So, but what is the good thing about word2vec is that it can produce this type of knowledge. For example, as you can see here, once we represent, for example, words in this embedding space, we will know that king and queen will be actually very close in this embedding space. Similar the things that man and woman, and operations like, actually there are many examples that if you, from the word king, you subtract the word man and add the embedding woman, you will get something very similar to the embedding of the word queen. So these are the type of relations that are presumably obtained by word2vec. And actually it's true. I mean, depends on the data that you use to train, but normally if you have plenty of data, you will get very good embeddings. Some recommendations that the authors of the paper give if you want to train your own embeddings is that, well, something that you have to take into consideration is that as many neural network-based methods is very sensitive to the training parameters. So you have to be very careful about this. This word2vec can be trained either with hierarchical softmax or negative sampling. However, for example, this hierarchical softmax is recommended for cases where in the data set there are many rare words, right? The other thing is, for example, the quality of the produced embeddings is better if we consider high dimensionality vectors between 100 and 1,000 units. Yeah, that's the recommended number. Most of the embeddings that are freely available are normally 300 dimensions. It's like a very common number in this type of representation. Regarding the context window, well, the authors recommend a context window size of 10 for the skip-gram model, while a context of 5 for the CBOW method. So if you are interested, perhaps these tips could be useful, but again, I will recommend you to read more papers that have trained from scratch these word embeddings. But okay, so word embedding, word2vec, sorry, was the beginning of everything. Actually, as I was saying before, it's for some can be very old. It's word2vec was proposed in 2013. Since then, many other neural network-based word representations exist. Here I show you the four more important ones, perhaps, in my opinion. Fast text, which is actually the evolution of word2vec, is also context-independent embeddings. The difference, the fast text with word2vec, is that fast text considers character level information, and this helps to identify, to be robust against very rare words, right? GloVe, which is also a context-independent approach. GloVe combines some advantages of latent semantic analysis and word2vec. More recently, in 2018, Elmo was proposed. Actually, this is, if I'm not mistaken, this is one of the first proposals that generate contextual embeddings. That means that this type of technique is able to generate different embeddings for the same word depending on the context where this word appears. And this is based on bidirectional LSTM neural network. And the most famous one, I would say, is BERT, which is also contextual embeddings and is based on these famous transformers architectures. And again, here I leave all the references where all the details of these methods are described. And this figure, perhaps you know, perhaps you have seen this figure before. This is a quick view of all the different type of words representations that have been trained or generated based on, for example, on BERT, on Elmo, or also we have something that use cross modalities like, for example, how to consider video. XLNet is also very famous and very common, but has some differences against BERT. So this is, again, I'm not going to spend too much time here, but this will give you an idea of the variety of models that have been proposed in the perhaps last 2 years, I would say. Okay, now as a final case of study, I will speak briefly about some exercise that we did actually here in EDAP with Shantipriya, which is fake news detection. As you probably know, the task is automatically detect those news reports that are actually fake. That means that contain information that aims to manipulate people for whatever reason, right? For this paper, what we did is we work with some news documents from Mexico, from some news sources in Mexico. From this data set, it's actually near 900 documents, and only I don't have here, but okay. I don't remember the exact number of how many of these were fake, but this is more or less the size of the data set. What we did here is actually we wanted to evaluate the relevance of deep supervised autoencoders in solving this task. And for that, well, I did not speak about supervised autoencoders in this presentation. I will not speak about that, but supervised autoencoders are basically representation learning techniques. So supervised autoencoder can be used also to learn word representations, although we use supervised autoencoders in combination with pre-trained encodings. In this case, for example, with BERT, and also with some traditional text representation as words and engrams characters. So the main architecture of our method is something like this. We have documents here. We extract some features based on traditional or pre-trained encodings. And these features become the input to the supervised autoencoder, which is actually able to learn a representation from this data. And also it's trained to identify the target class of the documents. So here is the reference if you want to know more about supervised autoencoders. This is a more detailed view of our method, but it's basically the same idea. Perhaps the only important thing that we did is in this part. As you know, BERT, Beto in Spanish is BERT in English. This BERT model is trained in Spanish, actually. So we did not did any fine-tuning of BERT. What we only did is to apply or to obtain the encodings for every news report using this pre-trained model, and we combine these features with some traditional representation, and that was used as an input to supervised autoencoder. So what we learn from here, that, well, as expected, BERT techniques, as you can see in this part, these B rows are the best results using BERT only. But when we combine BERT with some traditional word representation, with some traditional document representation techniques, actually we see some improvement, especially in the validation phase. So if you are interested in knowing more details, you can read the paper. But what we learn from this exercise is those word embedding work. Yes, it worked as expected. Actually, in the combination with supervised autoencoders, we were able to obtain the first place in this task. We were very happy about that. This happened this year. But what is the problem, or what are the consequences of this? I mean, as I put here, with great power comes great responsibility. There is a lack of interpretability. Actually, if I will go back very fast, as you can see here, one of the best results that we obtain is when we use the mean pooling strategy from these BERT encodings. What is the meaning of that exactly, or what is the interpretation? Is that what is could be something like this. What is actually working here is not the things that are capturing the attention from the BERT model. That will be my interpretation. And why is happening that? Honestly, we don't know so far. We actually planning doing some more analysis, because it's very difficult, even for the original author of BERT. It's difficult to explain what is actually happening inside this neural network. So if you have tons of data, you can do a fine-tuning. Don't hesitate about it. If you don't have this this amount of data, perhaps you will need to think in something else, which was the case in this example, where we combine pre-trained encodings with different techniques in order to obtain good results. Okay, so I almost finished. Some final remarks that I would like to add is, and it's not conclusion, because I already mentioned some conclusions before, but this will be something like takeaway message. So I guess that for you, that since you are here, working with language is very exciting, very challenging, and it's very motivating work. Language is constantly evolving. I mean, you can see it. You can see it in social media, right? People doesn't communicate the same way that we did a few years back. Now, with the pandemic situation, also there are new lexicon that is arising, right? In this scenario that we are all living right now. Also, well, as I was saying in the beginning, low resource languages are also a big challenge ahead, because this, especially for these big models based on big deep neural networks, that they require big amounts of data. So what happens with low resource languages? We don't know, and there is no clear solution about this. So another thing is that, well, I hope this is, I made my point. I hope I made my point here that text representation is a key aspect for every NLP related task. But something that I usually recommend to all my students is, first you need to look into your data. You get to know it, and then you decide accordingly. Perhaps it's not necessary to use a big transformer architecture for solving something that is, I mean, is not related, or is not necessary to do it. And also, this type of traditional, I would say traditional indexing, like technologies or concept-based representation, latent semantic indexing, well, this type of technology is still being used actually in the present by many companies. Many of the solutions that many companies offer are based on this type of technologies, and not in the very recent BERT or neural network approaches, I would say. At least in my experience, this has been the case. Well, the last couple of years also, well, have represented an inflection point for machine learning models that are able to handle text. Probably you hear about GPT-3s during this year, the release of GPT-3s. GPT-3s is also a big neural network, deep neural network with billions of parameters trained on billions of documents. But apparently, well, even though this type of technologies have helped to solve many NLP-related tasks, I would say that there are big gaps that need to be considered. For example, what is actually are these type of technologies are applied or can be easily applied in real life scenarios, real tasks? I mean, this is a question that I don't know how to answer, because it's difficult, especially because this type of technology is lack of interpretability. There is also a big discussion in recent ACL conferences about bias and ethics, right? I mean, all the data that are used to train these models contain some bias. This is not easy to avoid, right? Or what are the ethic considerations if we are speaking about health-related applications, for example? And also, what is the cost associated to this type of methods? I mean, we need to think also in sustainable NLP. To train this type of models is something that, at least here in Switzerland, even in Switzerland, we don't have access to this type of technology to train these models, right? So for me, if I go back to Mexico, well, this is even worse, right? It's very costly. Not everybody has access to this. And finally, another question is, are these big models really understanding the language, or they are only very good manipulators of the language? This is something that I will leave here to think about. I mean, and this is a quote that I took from this paper from Emily Bender, which says, meaning cannot be learned from forms alone, and even large language models do not learn meaning. They learn some reflection of meaning. So this is something to think about. Thank you all for listening. I hope this could be interesting for everyone. And if you have any question or if you want to contact me for any specific paper that I show during the presentation, I will be happy to share. Thank you.
Thank you, Dr. Esaú, for your good presentation, nice presentation, and informative case study based presentation to our participants. Definitely, they will be benefited from this. So, anybody having any questions, kindly just ask to Dr. Esaú.
So, I have a question.
Yes, yes.
Sir, thank you for this amazing lecture. It was very, very informative. From one of your slides, you showed a contextual embedding based on the context. So, sir, it piqued my interest that whether can we actually understand the emotion or the sentimentality of the text using the embeddings? Is that what you were aiming for?
Well, in the cases that I showed during this presentation, we did not did any related to sentiment analysis, but yes, there are plenty of work that have tried to do sentiment analysis using this this type of embeddings, BERT embeddings, ELMO, even Word2Vec. I mean, they have been used for that for sure, but well, I don't have experience in that case.
Okay, sir. And so one more thing, sir, there's this recent technology released by Facebook, which is like Wave2Vec. It is mostly about audio, I think. So
Wave2Vec.
Yeah. So
yes,
I wanted to know your opinion about it, about this technology.
Well, that's not related to speech, right? For what I know, the idea is to generate some representation given as input some speech signal. I don't have the experience with that because I don't work with speech, but probably Petr will speak about that. Tomorrow, I think there is a talk from Petr Motlicek, also from here, from India. He's more expert on that field.
Okay. Thank you, sir.
No problem. Thank you.
Thank you very much. So we'll take a break for 5 minutes. After that, I will ask everyone to join the inaugural session of formal inauguration, which will be started at 4:30. And kindly, I request everyone to on your videos during that session, so that it can be recorded properly and we can send to AICTE. Thank you very much. So we have a 5 minutes break. Dr. Esaú, after 5 minutes, we will join again for the inaugural session.
Okay, thank you.
Thank you very much.